Good evening, everyone. We're just waiting for other delegates to arrive, so we'll wait a few minutes as others arrive. Hi, good evening, everyone. We're just waiting for delegates to arrive. There's about 30 people present at the moment. We're not due to start until 7 o'clock, so we'll just wait a few more, or another minute or so. Well, it is 7 o'clock, so good evening, everyone. My name is Professor Phil Rubini. I'm the chairman of the Hull and Humber Region Committee, part of the Yorkshire and Humber region. And this seminar, entitled Electric Air Racing, is a joint seminar together with the local region of the Royal Aerospace Society. And so I imagine we've got delegates here from both IET, the Royal Aerosoc, and I hope from people elsewhere as well. The speakers this evening are Richard Glassock and Jeff Zaltman, and I'm going to let them introduce themselves. So if I hand over to Jeff, if you'd like to introduce, and the way we intend to run the seminar this evening is that Jeff and Richard will deliver the presentation together, and then we'll handle questions after that. And I'll try and field questions. So if you do have questions, you can put those into the Q&A, which you can see at the bottom, and we'll go through those at the end. Just to advise, this seminar is also being recorded and will be available at a later date as well. So thank you. Jeff, if I hand over to you.
All right, thank you very much, Phil. And guess I shall share my screen as I'm introducing myself. So thanks again, and thank you to everyone for taking the time to hear what we've been up to and to take an interest in what we're doing. We're really grateful for that. I guess just to introduce myself, I'm the founder of RAeS, and founded the company about 3 years ago. But actually before that, I've been involved in airplane races for almost 20 years. So I've been organizing events all around the world on most continents in different formats of air racing for a long, long time. And of course, moved into RAeS a few years ago. So I'm going to be telling you about RAeS, give you an overview of the project. And of course, in a nutshell, as you will have gathered by now, it is the world's first electric airplane race. Now, as Phil mentioned, I'm going to give you kind of a bit of insight into sort of what we do and why we do it, and kind of explain the sport and what our objectives are. But then I'm going to hand over to Richard, who's going to go into a lot more detail on, in particular, a specific project that we're working on together with the University of Nottingham, and some other exciting kind of spin-off projects. So let me start with a bit of background. What we're really trying to do with RAce E is, well, the first stage is effectively taking air racing into the future. But in doing so, we're trying to take aerospace into the future by converting it to electric propulsion. What we really want is RAce E to be it's a test bed. It's a platform for the entire industry to innovate and develop the technology, and it's kind of a playground for the aerospace industry to be developing. The easiest way to kind of draw a parallel is that of Formula E. Most of you will be familiar with the electric car races, Formula E, and there's also Extreme E and E1 now with powerboats. We're basically doing for aerospace and aviation what those events are doing for automotive and, of course, E1 with boating. So we're really following that Formula E model, and both in a sort of a business model as well as in sort of objectives and a mission. And at the end of the day, it's also an exciting motorsport. So that's really what we're trying to develop. It's a thrilling, real, true motorsport. On that note, I'm going to give you just a short video here to give you a little bit of an idea about what we do.
So close, this battle between the two of them, just meters between the two planes.
Are you ready to experience the evolution of air racing? Welcome to the world's first all-electric air race, RAeS E. Prepare yourself to witness the exciting future of aviation and motorsport right now. RAeS E is a pioneer leading the charge in the electrification of aerospace. It is the only electric air race series with manned aircraft pushed to their limits in a real-world mission to win. Pure motorsport in 3 dimensions. Aviation is going green, and RAeS E is at the center of the revolution, creating a platform for the industry to move forward and accelerate the technology that will help save our planet. New concepts in electric propulsion and hands-on partnerships with aerospace and automotive leaders allows RAeS E to reshape the e-mobility and transport industry. The spectacular and action-packed competition will see top pilots commanding leading-edge technology racing head-to-head at speeds of up to 400 kilometers per hour around a tight circuit just meters above the ground. The true motorsport for the future by the world's leading air racing organization. Are you ready to meet the future?
It's a dynamic sport, and there's nothing like it in the world.
All right. So hopefully that gives you a kind of a flavor of what we do. Now that video is important. In fact, I should probably qualify and say what you saw there was called Formula One air racing. It's an existing sport that we organize now. It's a sport that actually has a history of about 75 years. And we've been organizing these events with combustion engines, conventional aircraft around the world for a number of years. And what we're doing, the reason that's important is because we're using the exact same format, the race format, as we do in the current Formula One race for the electric. We're, of course, just changing it to be adapted to the electric propulsion. So what that means is, as you can see here, it's a series of laps around an oval circuit with 8 airplanes all racing together. First one across the line wins. The key difference, I guess, besides the powertrain, is just the number of laps. In Formula One, we do 8 laps, and in RAeS E, we're going to be doing 4 laps. And so this is kind of the fundamental premise, is that motorsport is itself a catalyst for innovation and for development. And we know that. In motorsport, automotive motorsport, for example, and other motorsports have a long history and a proven track record of bringing new products to market. And air racing is no different. And we actually have over 100 years of history of doing this as well. In fact, I like to use the example of the Spitfire, which of course is, perhaps the most successful warbird, certainly of World War II, one of all time. That actually was developed first and solely for an air race. It was developed for the Schneider Trophy in the UK, and it was built as an air racer. And that's what it did through the 20s and 30s before it got repurposed for war, of course, under the necessity of doing that. So there's a lot of case studies of taking technology from air racing and moving them into the private sector, and well, in that case, military sector. But that's exactly what we're trying to do now. We're trying to do that same transition of technology again. And we've got a lot of partners on board that have agreed with that, validated that sort of a premise with us. We've got Airbus came on board a long time ago as a founding partner. ANSYS is helping our teams use their simulation software to develop the aircraft. Obviously, University of Nottingham, which you'll be hearing more from in just a moment. A recent one was Casero. It's a German aerospace engineering company that just came on board a few weeks ago to help us develop one of the classes, which I'll mention again in just a few seconds. So, these are really, really great, again, validations of people seeing our vision, be able to develop the technology that's going to be relevant and meaningful to the aerospace industry. This slide, you don't have to worry too much about it. It was just to kind of mention that it's a formula race. So the idea is that we write the rules, a list of criteria, it's a formula, and then the teams take that criteria and they can design in a very open fashion how they want to. They can connect those dots how they think is going to come out with the most optimized solution. So that's our kind of principle there. Here we just draw out a couple examples of that. Now, as I mentioned, the rules are starting with the existing racing rules. We're not trying to reinvent the wheel. We're just repurposing it for electric. So we have electric propulsion requirements. There's 150 kilowatt power max limit with a boost option, which is kind of an exciting option. They get to boost for 30 seconds. It's a shorter race. It's 4 laps. They typically do it at full power, full throttle. And then they have to have, of course, a reserve left over to land. And the top right point there is really important. It's an open platform. We're trying to keep it as open as possible so that every stakeholder in the industry can join. Now, since the beginning, everything you've seen up to right now, everything I just was referring to is what's called the open class. But we've actually added 2 more classes of race. So, based on the success of that and the needs of the industry, we've actually expanded. So the open class is, as it sounds, the open class is quite open to any manufacturer, but the performance class is what we're starting with that company, Casero, that I pointed out a moment ago. And what we're doing here is we're actually taking under our roof, in-house, the development of 8 race aircraft, electric race aircraft that are going to be retrofitted to existing race aircraft. And that's really important because what we can do is we can, not only do we own the IP, but we can, centralize it. But really the important thing is that, we're going to have, this is why we call it the performance class. The idea is to have 8 sort of standard powertrains, but then allow the teams to modify them, and certainly to modify certain areas like cooling systems and inverters and programming. So there's going to be a lot of really interesting comparisons from like-to-like products that are used and operated and modified and maintained and run in different ways. How do they charge it for the race? What's their strategy for charging it? How does that affect the outcome? So, it's really about performance and optimization, which is really exciting. And then, of course, as you see there, a vertical class, an eVTOL class, which, as you can imagine, will be a very exciting part of what we do going forward. I'm not going to go too into detail about the tech and the teams, because Richard's going to give you a lot of really meaty stuff about one of our projects. So he's going to handle that bit, but I just wanted to kind of mention a couple teams that we have, really, really advanced. Now, this is our Nordic team from Norway. They are actually ready to go. This plane is in the hangar waiting to fly. It's just awaiting the document from the CAA. All paperwork's been submitted. So as soon as we get that document, this plane is going to do the first ever test flight of an electric race plane, hopefully in the next couple of weeks before the holidays. So that's going to be really, really exciting and very big milestone for us. This is an example of the Swiss team. So what these guys are doing, it's exciting also because they're doing a completely ground up design. They'll also be flying early in the new year. and they've done a completely, completely fabricated aircraft in their own works. What I want to mention about both of these teams is that these are both aircraft manufacturers that want to produce electric airplanes. So what that's done for us is proved exactly what our mission is, that manufacturers will see this as a place to develop and hone products and aircraft that they can actually bring to market. So these guys, PRNFs, actually want to produce and sell this particular plane, whereas the Nordic team, as you can see, they're retrofitting an existing Casset 3M racer. So what they're doing is they're focusing on the knowledge gain from the powertrain itself and certain technologies that they're instituting in this powertrain, and they want to transfer that to seaplanes, which they produce. Excuse me, electric seaplanes. Now, none of this means anything if people aren't going to adopt the usage of electric airplanes. It's all good and well to build them, and it's fantastic, pat on the back, but we have to have passengers, right? Where they have to find a place in the market and amongst users. So it's really important that we use RAeS also, not just as a technology platform, but as an engagement platform to reach out to audiences and try to explain the technology to them, make them familiar and comfortable with it and enthused by it, get them excited by it, so that, when they have a chance to go in an eVTOL across town or hop in an electric airplane between London and Paris, they're already excited by it. They're already familiar with it, and that, no one asks any questions about it. So to us, that's really important. That's where we have a test bed and contact with the end user. And we do that through, of course, media. We're very successful in our media on the RAeS 1 side. I should have mentioned RAeS 1 is our brand for the Formula One air racing that we do. So under RAeS 1, we've got really successful television coverage, media coverage, and that is transitioning and ballooning for RAeS E. So RAeS E is getting tons of attention right now, as we think is justified, and we're really grateful for that attention. And again, that helps us take our message out to the masses. Oops. This is just a short video. I'll just play, give you another flavor of it. Now, it's worth mentioning there that aircraft there, obviously it was a rendering, but it's a rendering of an actual CAD model, that a design that our Dutch team, which is really fun because it's a team of university students that designed the powertrain and also ground up design aircraft. As you can see, it was a contra-rotating propeller. They've instituted some really interesting concepts into that as well. So we made that video out of their design to help them get started. So anyways, that was my kind of quick overview of what we're doing. In front of you here are obviously just kind of a few quotes from some of our partners, but I'll leave it there, and I will pass over to Richard, who's going to go into a lot more depth on a very exciting project that he and I have been working on between RAeS and the University of Nottingham. So I will stop it there, and thank you all very much.
All right, thanks, Jeff. I just want to make sure you can hear me all right, and I'll start sharing my slides, and I'll give you an intro once I get my title slide up. But yeah, thanks very much for IET and Aerosoc to bring us back here and let us show you what we're doing. Let me just queue it up. That should be good to go. And if you could just let me know if you're if you're seeing this come through all right. Because I can't hear anyone, but
Yep, Richard, it's fine.
all right, that's great. Yeah, so my name's Richard Classic, and I'm just had 5 years of as a research fellow at the University of Nottingham. Now I'm working for a small commercial company in North Yorkshire called Condor Aviation. But I'm still very much involved in the project that I'll be telling about, and also some others. So just as a general flavour overview of the projects that I am doing and some of the other personal kind of background that I've been involved with, and one of the the sort of reasons why I've ended up here doing this stuff. Background, I've done just general aviation flying, not a great deal. I'm actually currently renewing my PPL here at the moment, hang gliding back in Australia, where obviously I'm from, and a few of the interesting projects that I've been involved with both at Nottingham and before that. So I started my research in hybrid and electric propulsion aircraft about 20 years ago, in hybrid electrics for Aerospace, and that's why I'm here. That's what I'm bringing forward to the situation here. So this project that I'm discussing that is still being taken forward at Nottingham was with Jeff about 3 years ago. We wanted to do a demonstrator program in the university under a internally funded program called Beacons and Future Propulsion. So it came up, I was asked to look around for a project that would be suitable to electrify an aircraft, and preferably one that was actually going to fly. I came across RAeS, which is really exciting and a really good fit. I spoke to Jeff about things and what we might be able to do. And so we decided to take an aircraft and retrofit it as a demonstrator for basically to understand what the pros and cons are, get a feel for the technology, utilise some of Nottingham's pre-existing technology. So we got Jeff's aircraft there, which is a Cassett Racer, and registration is G left. And we got it delivered to Nottingham, and we brought it into our labs at the university. And as you can see the picture in the middle there, one of the first things we did was to take the engine out. We also had to take a lot of data from the aircraft, and we weighed it and noted down all the various systems. But we wanted to divide the project into two main phases, and now phase one is pretty well finished. Obviously a little late, but we've now basically delivered that demonstrator. I'll show you some of the pictures of it and go through the design of it. And it's not designed to be optimized for the race, really. It was designed to be a practical way to get a system running that would suit that aircraft. We'll be able to fly the aircraft, but it's not necessarily going to be to the top performance level. And it will show us all of the ways in which we could optimize the system as we go forward. And that would go into phase two, where we could design and develop internally at the university a fully bespoke electric propulsion system, rather than only integrating mostly commercial off-the-shelf components. So that's still the plan as I know it. And now we've finished phase one, and phase two definitely there is a lot of room for improvement. In fact, the aircraft that you saw that Jeff presented from the Team Nordic folks is actually the same type of aircraft. It's a Cassett, and it does illustrate quite well some of the optimizations that we could talk about. But in this case, all I wanted to do was retrofit a suitable electric motor, commercially available, known to be reliable, pretty close to the right power output to replace the engine that we took out, which was a very standard Continental 0200 engine, which is the class engine for that RAeS 1, and make sure we replicate the performance. And obviously we have to try to replicate within the weight and balance limitations of the original aircraft, because we want the original aircraft to fly very close to how it used to. albeit with a much shorter endurance. Clearly, the battery capacity is the main limiting factor. But the amount of power on board a racing aircraft, or any aircraft really, in terms of its ultimate performance, particularly in a racing circuit, is not strictly governed by the amount of power. Sure, you want to have the most power you can, but there's so many other factors in there, and particularly the drag. And the drag is very also dependent, obviously, on the weight for generating lift and also for going around the turns. I just have in this slide, just of note, there are some standards that have been developed for various components of the system. They're still in development, but the EASA has now got standards. And one of the outcomes of the project, and one of the ongoing outcomes, which is really exciting, and today even we've been discussing with people from the CAA in the UK and also Light Aircraft Association, because it's all helping develop their own standards, because they know electric aircraft are on the way and they want to help facilitate that. So what kind of motors are kind of out there in the commercial space at the moment that we could draw upon to use? Well, I'm just illustrating several here from various suppliers. We did end up choosing one that's from a UK supplier. This is on the top left, EASA motor. They're pretty well designed and put in a lot of cars these days. There's several European suppliers that are quite popular, and I think you saw one of the MRAX motors that's on the top middle here installed in one of those examples that Jeff provided. One of the bigger companies in France or Europe, Safran. Obviously, down on the bottom row here, there's several Rolls-Royce electric motors. And this on the bottom right is an example of how, and I'll refer to this later, how the different architectures of electric motors for aerospace is really important. And you can see this one's got a very large diameter annulus in the middle of it. And there are some reasons why that can be very useful. So in terms of the component level stuff to change out in the cassette, obviously we pulled the engine out and any other associated equipment, the fuel tank, engine controls and instrumentation. So what has to go back in? If we just sort of go around so clockwise, we've got there has to be a pilot interface, and this is in order to control the inverter. It'll end up being a potentiometer or some other signal kind of device like that. We've got a pilot information display, which is very, it's just an LCD type screen, but it interfaces with a computer. And this particular one comes from a motorsport company, Motec, which is very interested in seeing how this will work in an aviation space, but it's again in a sports racing space. So far pretty good. We can fully program what the instrument displays. There's obviously some very important differences between what you have in an ordinary gas aircraft versus an electric aircraft. You want to know your battery levels. You want to know your temperatures. You want to know, the power output, maybe the torque. There's other quantities that you can display that might be different from an internal combustion engine. The motor itself, that has to go in. In this case, not in every case, but it's one of the factors which is of interest. This case needs a cooling system for the motor. Can run at much higher powers if it's got a liquid coolant flowing through it. So there's a pump, there's a heat exchanger for that. The inverter itself, predominantly the motors are brushless permanent magnet DC motors. Well, DC until it gets into the inverter, which actually creates the signal and the drive currents to drive that motor. So you've got to have an inverter. Again, typically if it's a high power inverter, it'll need a cooling system. In this case, again, it's a liquid cooling system, and it's a separate circuit. There's a different type of coolant. The coolant in the motor is basically an oil-based type coolant, and you can use a water-based coolant in this inverter. Then we come along to the battery system. I'll detail this a little bit more, but you've got cells in an array. You've got to have a certain series and parallel array of the small cells there. Different types of cell are used in different EVs. In this case, we went for the pouch type lithium polymer cell. I'll show you some more of that. A lot of the EV and aircraft EV people are using cylindrical cells, and that's fine. There's pros and cons to them. You can see these boxes here, these black boxes. So these are going to contain our battery system as we install it to the aircraft. They're fireproof boxes, because one of the key risks is obviously thermal runaway in the battery system. Probably most people realize that about high power lithium systems. And then there's obviously a need to charge the system. So the charging is and discharging actually on the ground, if and when necessary, is really important. And that includes a battery management system that's on board the aircraft, which basically monitors and can control the voltage levels at pretty well down to the cell level. So all of that stuff we've got to architect together, arrange, fit, and build into the aircraft and try to get it to end up weighing something that's reasonable. So battery system, as I said, we decided to go for these pouch type cells, and I'll show you why in a moment. Basically because the university had already a program that used this type of battery technology. So we get commercial off-the-shelf cells, try to select them to be, suitable for the amount of power and the energy density and the power density that we expect to use. They have to be lined up and put into various parallel configuration and series configuration. We put them into modules, basically sub-modules onto a circuit board with bus bars to connect all of the tabs of the cells, and also some places to plug in monitoring systems. So it's a circuit board that's designed and built in-house at Nottingham. And we put them together, the modules, into little sub-packs in order to fit them into the boxes, in order to fit them in the aircraft. So we didn't want to change the airframe very much, minimal that we could. So we designed these packs individually. It's an unfortunate thing to have to do, but we really wanted to keep it within the original mold line of the aircraft, so we didn't have to muck around too much with the cowling and the structure of the aircraft. So there's 4 boxes there which will be linked together, and they fit into effectively where the original fuel tank was and the original cylinder head banks inside the cowling. And this is suboptimal. As in the previous presentation, you saw a better layout, really, more optimal anyway. But this is a low-risk strategy that we took. So we're keeping the original engine mount system, and this is the only way the batteries will actually fit in. Whereas on the other presentation, you saw the electric motor was actually mounted directly to a battery box. The battery box was a structural component, which is clearly a more optimal way to do it. But going forward, this is probably where we would go to. You could even integrate the external skin to the structure of the battery compartment and the motor mount. So yeah, this is the background of Nottingham in EV racing. TT Superbikes operated the Isle of Man, Hassan, and Pikes Peak Hill Climb, and very, very successfully so. And this is completely done, design and built inside the university, something about which they're obviously very proud. And this gave us the confidence to know that we would be able to integrate and develop a system for RAeS. Very similar kinds of size, power, and weight in the bike as to the aircraft. As a matter of fact, the bike could actually take more battery because it's less weight sensitive. I think they ended up having nearly 200 kilograms of battery on the bike. I think it was something like that. And a different optimization problem, but again, it's going around a lap circuit, and you have to optimize not just maximum power, but you have to optimize the whole energy flow around the circuit. So, you can look into that. I'm not sure if that racing class is going at the moment, but that's where we came from. So the mechanical design of getting that particular motor, the ASA motor that I mentioned, into our aircraft with the reasonably minimal structural modifications. So we decided to use the original engine mount structure from the 0200, and then adapt a new structure to fit this YASA. Now, the YASA motor, as it comes, this particular version, you put a spline shaft onto the rotor internally to the motor, and you can't load that spline with anything else but torque. It hasn't got the bearing system to enable any angular loads or thrust loads. So we had to design and develop a bearing mount system for the propeller shaft, which you can see at the front of the motor, and then a means to carefully take stress from the propeller load through the motor housing and into the aircraft structure. And that has to be done quite carefully because the motor casing is not really designed to take those loads either. So we've spread it all out. We put it into an FEA according to the kinds of loads that we expect to see on the propeller. And it's overbuilt. It could be optimized further. It's heavier than it needs to be, but we believe it'll be a good, safe way to go for it, and we'll get the results we need. It is an interesting design in that the shaft housing system here can be used independently of this motor. We could use the same mounting system of the shaft for other motors, either direct drive or geared or belt driven. So one of the trade-offs is having a motor size and a torque relationship for the particular RPM that the propeller is best at. Comparatively low RPM compared to the automotive experience, but it is possible to get a smaller, lighter motor running at a higher RPM, and then you just have to run a gear drive. So we can do that with this system in the future if we want to. We also made a large diameter through the annulus of this shaft mount, which can later be used for running a shaft, maybe control propeller pitch, potentially for running counter-rotating, and there's other options there. It did require a bit of trade-off in this kind of bearing selection and other things, but again, I think it's good. We can use this for other motors and other designs going forward. So the process was back about a year, maybe 2 years, a year and a half. The Cassid is a small airplane, especially once you take the engine and the mount off it. So I was able to transport the aircraft to our partners who were doing the Aerospace, the mechanical assembly for us, which is East Midlands Helicopters at just near Nottingham. And this was a good idea for us. The university is not an aerospace manufacturing or design or maintenance operation. So the helicopter maintenance organisation knows all of the ins and outs of how to do aviation specific, aviation standard fitting of all these components. So they helped us out really well. We processed that. Then after we made sure it fitted according to our design work, we took the motor back out and we put it into the lab at Nottingham in Power Electronics and Machines laboratory on a dynamometer, so that we could test the parameters, the control of the motor. There's programming, there's software, there's cooling. So we wanted to get a handle on how that's going to perform in a controlled environment. There's a video here which I hope will play. It's quite short, but it shows you it running in our labs. Yeah, so that was quite a useful process. We got a good lot of data out of that. We're confident that the motor is going to run up when we reinstall it to the aircraft. The control system via the software and the little computer that basically interfaces between the pilot and the inverter worked. And then we got it back in the aircraft for the final fitting and assembly. The cooling system had to go in, the controls, the pilot interface, you can see there on the bottom right. We're going to reinstall some of the original instruments, not all of them, but you do need to have some of your original aircraft instruments, obviously your altimeter, airspeed indicator, and things like that. So that's going to go back in, but you can see the pictures here are nearly complete. We are still waiting on our battery pack to be finally integrated and solved. We did run the system on a ground power unit in order to get the initial test runs done. But the battery pack is currently very close to being completed, and then we'll just fit that in and do the full power run-ups and testing for that system. So this is a little video that we took about a month or two ago. Shows you the first running of the aircraft.
So the project is a conversion of a small pylon racer aircraft, single-seat aircraft, from petrol engine to electric propulsion.
It is a new research, it is fully electric aircraft, and it is world-leading technology.
We wanted to keep most of the airframe original. It's a much more pragmatic and safe way to do the problem. So we just changed out the engine and the propulsion system.
To scale this up into larger aircraft, there would obviously have to be a lot more developing testing at this scale, but realistically this is where we need to go. So to develop it at this stage, it is going to get bigger.
Right, so excuse me. That shows you the system that we've developed. Didn't have this water. Yeah, so that's now in its final stage of integration. As I said, there's more to do. In the meantime, as we were doing that, I was able to help Jeff and RAeS and some other partners show what this will evolve into and how it's going to look and run with another aircraft with a different propulsion system. But it's the same kind of motor. It's just got two of them back to back to run counter-rotating propellers. So there's a lot of interesting potential for counter-rotation, and electric motors make it relatively straightforward and easy as compared to the historical precedent. There aren't many counter-rotating propeller aircraft. There are some in service and they've been investigated, but one of the big problems is the mechanical complexity. So with electric motors, that problem comes down quite a lot. If you've got these motors that can have a large diameter annulus in the middle of the rotor, a hollow center, you can run the rear shaft through the whole lot and the front shaft through, and then you can run these two propellers. So this system was tested quite extensively by Contra Electric. We've got it here now in our base of operations, and it's ready for more testing and development, potentially putting into other aircraft. It's a little bit overpowered actually for the Casset, but there are other aircraft that suit it. And this is about how the RAeS program starts to develop systems that will be useful commercially. Starting small in the general aviation domain. So one of the research items and commercial items that I've been looking into quite a lot over the last 10 years with skydiving partners who runs big skydiving centres is how is electric aircraft going to look to them in their business? What's the performance outcome? And in fact, this is really exciting because you can expect really better performance than the conventional engines. There's a number of factors that lead toward that. Not least that the skydiving operation is really hard on engines. You're really pushing them hard, full power climb through, maybe 10, 12,000 feet, and then immediately a rapid descent through the thermocline and, with shock cooling issues and so on. Much easier to handle that with electric motors. The other thing is that potentially you can put a lot more power installed into the aircraft. And for this application, you want power, you want a climb rate. So climb rate is really directly proportional to power. And if you can get more power on board and it doesn't use more energy for the whole job, in fact, it can use less energy because you can run the aircraft more efficiently, then it's brilliant. Obviously, the battery capacity is still the main problem, but in some of the studies I've done, it indicates that you can do a climb to altitude, like a decent altitude for the skydiving operator, 12,000 feet. You can take an aircraft like the Cessna 182 as an example, it'll typically take anything up to half an hour to do that climb, not less than 20, 25 minutes. If you put in a serious amount more power, you can get that climb done under 10 minutes and possibly only 5 or 6 minutes. In order to run a lot more power on an airframe like that, you can't do it with a single rotating prop. The amount of torque, the size of the propeller and other factors will, it'll need a lot of modifications to even be controllable. But with a counter-rotating propeller system, there's no residual torque, there's no very little residual slipstream effect. And so that's super exciting. So I think we can look at putting 300 kilowatts into a 182 size aircraft when its conventional engine is not even 200. So radical increase in power. And there's a picture here of another way you could potentially develop by putting electric motors on the wing, battery pack in the nose. And electric motors are much, much easier to install, structurally much easier. Even the systems that you've got to supply to it to control the energy source and all of that, way simpler. So I think that's an exciting way to go, and RAeS is leading that and providing the impetus and getting people to develop the systems. I'm interested in some larger aircraft in hybrid and electric. This one is a design that I've been working on with a commercial client and partner for really 10 years, but originally it was going to be just a conventional gas turbine engine to replace a Cessna Caravan, to have a PT6 engine. I wanted to look at how it might be if it was hybrid and electric. So one of the first things you can do, you can put electric motors on the wing, you can triple your disc area straight up. You can run a smaller gas turbine engine. You can run that gas turbine alongside the electrics out of a battery. You can use the gas turbine to recharge the battery. You can charge on the descent using the propellers as wind turbines, and you can read the paper if you're interested there. But that's the kind of outcome we expect. And that's just one industry example, but there is also transport, these motor designs that we're working on in the propulsion system designs start to add up into a larger format. They can grow into regional, sub-regional type aircraft. And I always prefer to finish with this slide, which is kind of my dream aircraft, which I came up with 10 years or so ago, as a hybrid electric gas turbine turbo electric aircraft. And it's a big motor glider. And the reason it's just a dream to be able to take a soaring flight with 6 passengers. So you're sitting at a club seating arrangement, a social arrangement. You can have a galley, you can have a coffee machine, and a pie cooker, tea and scones, a bathroom, and you can go flying, and you can turn the engines off, and then you can soar, and you can take thermals. You can use a natural orographic and thermal energy. And it's no problem to turn the engines off in a properly designed hybrid electric aircraft, because you've got instant power available. The electric is just, I need thrust, turn it on. A gas turbine or other engines, you need to warm them up, and you can't just cold start them and hit them for power. And to run a commercial operation, particularly over built up area, you've got to have a reliable propulsion system. So that's just an example. Happy to talk about that later, but it's a 40-meter wingspan, 4-ton turbo electric motor glider, and it happens to have an open canopy as well, because from my hang gliding days, I just realized how brilliant it is to fly in the open air. So that's actually the presentation finished, and we've got time for questions. So I'll stop sharing the slides, but I'm happy to go back and refer to them if you've got questions. And thank you very much.
Well, thank you very much, Richard and Jeff. There have been a few questions coming in whilst you were talking, Richard, and Jeff was doing a manly job answering the questions in the Q&A. There are a few which are perhaps specific to yourself. So for delegates who are there, if you do have questions that might have arisen, then please do put the questions in the Q&A or in the chat, and then I'll try to lead and pass them on to either Jeff or Richard to answer. So there are a couple of outstanding questions. Well, Jeff's answering one of them now, apparently, but I don't know whether... No. So, Richard, in converting the cars, I guess that's the Cessna, isn't it, from gas to electric, did you maintain the weight and centre of gravity of the original design to maintain the basics of the original clearance? That was the question.
Yeah. So I think the question is referring to the Casset, which is the race aircraft. And the answer is yes. We need to be very careful about how we maintain the gross weight and the balance in particular, and that is a problem. It's a very small aircraft, and there aren't too many margins on that. We have had to compromise, in our case, the battery capacity quite a lot to prevent a nose-heavy aircraft and to prevent too much mass. It is a matter of wing loading. So the class has got a minimum. The original class has got a minimum of 66 square feet wing. And so naturally, just about all of the races designed and built for that class have got the minimum wing area, because that'll ultimately result in pretty well a minimum drag. But it is possible to put a larger wing and different wings on those Cassets. So there is a lot of scope for development of the Casset. It's to develop different wings. You would be able to have an optimized wing area increased to handle more battery mass. And you could also run the batteries in the wing. So we put the battery where the fuel tank used to be and where half the engine used to be. And there is actually a reasonable amount of space there. And that the other example that from Team Nordic there showed you how you can do that. But there are some limits before you would have to start looking at a larger wing, because the main limitation there is the wing loading, and that leads into problems in handling, really, the stall speed, taking off and landing safety, as well as the efficiency around the circuit.
Okay, thank you. Another question was, what is a typical two-bladed propeller size in terms of diameter and pitch?
Okay, you got me on the specifics of that, but I think our props, it's less than 2 meters. It's something like about probably 1,500. It's interesting because the propeller design is intrinsic to everything else. Like it's got the balance between the characteristics of the engine or the motor, the characteristics of the airframe, the aerodynamics of the aircraft, the RAeS system itself, the type of speed and turning diameter and radius and factors like that. In general, you want to have a larger diameter propeller for efficiency, turning at a lower RPM. But you've got then clearance issues at the front, particularly tail dragger aircraft like that. You've got to be able to have a minimum clearance to the ground. You don't want the undercarriage to be too long. So there's a number of trades there. And it also, in this case, it's a fixed pitch propeller. There's some interesting things about fixed pitch versus constant speed or variable pitch propellers, and how that works out with electric versus internal combustion. What I was going to say about that was that it's a variable, but in the existing class with the gas engines, one of the tricks they do to increase the amount of power they can use, because it's a fairly standard engine, is they increase the RPM of the engine. And if you can increase the RPM and you can maintain the amount of torque it's producing, then you can get more power out of it, even though it won't last as long. And they tend to put very small propellers on those race aircraft, so they get the RPM from the standard. I think it's roughly 2,500 is the maximum that it's rated to do as a certified engine, and they can run them out to 4,000 RPM, and they can actually get more power out of it. And even if the propeller is less efficient, they can overcome that with the amount of power. And clearly, fuel burn and fuel consumption in a 5-minute race isn't the critical issue. So there is a lot of interesting propeller development to do, and having the electric propulsion changes the dynamic of that quite a lot.
And as another question, you'd mentioned that the electric bike you're showing had 200 kilograms of battery. What's the typical weight of the battery on the plane?
Yeah, so as it comes out, I think once you remove the engine, the other associated components, you've only got about 120 kilos to play with, maybe a little more. But and that depends on how you've done the structural integration. So in the cast that we've just put together that I showed you, it's not much more than 100 kilograms, and that includes the enclosures, all the wiring, the circuit boards, the bus bars. There are contactors inside. There's a fuse system, the BMS system, and sort of distribution wiring. So you end up with, if you can get better than about 70% of that mass as your actual cells, then you're doing really well. But that's one of the issues. So the short answer there is I think we've got about a 100 kilogram allowance on our battery, because we've got the cooling system, we've got the original engine mounts, we've got those other brackets, we've got the extra propeller shaft mount adapter, and that will get us to the gross weight and just within a CG range. We may have to put the service battery, you know, for the instrumentation and the pumps in the tail to get it to balance properly.
Just there are other questions, but I was going to just for Jeff, because I think this is Jeff's question really. What sort of budgets are the teams operating on?
That's actually a very good question. So that was actually something we asked ourselves before we even had any idea about what those budgets could be in terms of setting up the rules. That was one of the challenges with setting up the open class, was the potential for big budgets to win or untethered budgets to, you know, to worry people. So that was actually interesting in our planning of the series. A lot of events like Formula E started with budget runaway in mind from the beginning when they set the rules and a standard vehicle. We didn't do that. We set it as an open because we just know that in aerospace budgets are limited anyway. So we weren't going to have that particular problem. But budgets are limited. So we have this problem. And to put a number on it, it's really hard to say, but it's the number I want to say, and it doesn't apply to every team. It can be less, it can be much more. It's about $250,000 is about what a team takes to get the aircraft put together. This is, you know, not charging for labor. This is the equipment and the components, etc., and to operate that team up to the point of it being race ready. So it's pretty modest compared to, you know, any other motorsport, which, you know, entry point would be millions of dollars. There'd be even twice that, 3 times that for a basic car in, say, Extreme E. So yeah, we're trying to balance that, trying to be conscious of budgets. Our goal with the performance class, when we build those airplanes, is to lease them and or sell them, depending on the model and the team, for a very modest amount. And that's kind of why we're doing that. We're setting it up to be much more economical, simplified powertrains, etc. So we have people's budgets very consciously in mind. And of course, it's a great platform for sponsors, as you would imagine.
Good, thank you. There was there was a question here which I think is going to be raised, not Ray Richards, if you can answer it, was from Ray. It's asked, what language are you using for computing on board?
Yeah, sadly, I'm not a computer or electronic engineer, more aerospace and mechanical, but so I cannot remember the exact answer to that question. I think there are a couple of proprietary interfaces that, for example, the supplier of that particular inverter is Sevcon. I just don't know the language that it's using, and then there's probably different layers in it as well. So I wish I could answer the question, but I won't.
It's not you, yeah. And there's 2 more questions, and they're similar actually. So I'll read both out, and then maybe perhaps as a close, both Richard and Jeff would like to answer these questions, and that will probably wrap up the evening quite nicely. So the first of the 2 questions was, looking towards a more commercially viable electric aircraft, do you believe battery technology is capable? And if not, how far away are we from having the technology? So that's one question. And the other question, which is related in a different way, given the relatively low energy density of existing battery technologies, isn't it more likely that future commercial aircraft will be powered by hydrogen or ammonia fuel cells? And are there any plans for an RAeS class using those power sources? perhaps the two of you would like to comment as your own views on that.
Yeah. Can I answer that first, because my answer is going to be much more simple than Richard's, and he's going to take all the wind out of my sails with his answer. So I'll go first, just to be real simple. Yeah, I mean, I think electric is for sure absolutely going to play an important role in the zero emissions evolution in aerospace. Absolutely, 100%. Even our partner Airbus, which you may have seen last year, switched its strategy to focus very much on hydrogen power. They still are backing us and partnering with us because, again, they see electric as part of that mix. And I think between, when you're looking at electric versus hydrogen versus other technologies, even versus combustion or hybrid, I think it very much does or will depend on the mission and the application, the platform or the aircraft itself. So I think lighter aircraft, we're going to see lots of electric aircraft, training aircraft, as we already see, Pipistrel and others, and they're just in production now. And I think there are going to be some perhaps longer haul, which the current technologies, yes, won't be viable for certain middle and long haul ranges. But of course, the battery technology could change and completely change that dynamic. I just wanted to add that one of the reasons we launched RAeS was because we looked at battery technology, and obviously we're in aerospace, we're much more inhibited and limited by the weight than in any other sector. I mean, a car, you could put a heavy battery on it and it'll go. It's kind of a question of how fast it'll go. It'll go. In an airplane, it might not lift off the ground. It certainly won't carry any payload. So it's a completely different question, and we're much more constrained by that. But what made it exciting to me was that air racing, I didn't immediately saw, but when I saw it, it was an immediate click that, hey, wait a second, we do have the technology right now to do what we're doing, what we're proposing, which is air racing. So it is short blast, very short races. There's a limited utility to it in terms of the aircraft performing a mission, but we can use this as that catalyst to to develop all the different technologies that we're looking at. So when we realized that actually air racing, the format of air racing, lends itself very well to electric, I knew that was a starting point. So that, yes, the answer is yes to the question. Right now is the perfect time for air racing to take it up. I think it's also for light aircraft. And then it's probably a mix going forward. But I'll see what Richard has to say about
Richard?
That.
Yeah, well, I agree with you, Jeff, and it really does depend. Their insightful questions are, by the way, quite good issues there. So what is a commercially viable electric aircraft? Well, I would say that they are commercially viable already. It just depends on what you are talking about in terms of the role and the mission. So clearly, for large, big, heavy stuff, it's nowhere near it. But for small, light jobs like the skydiving, or for glider towing, or in fact for public transport at very short range, short endurance. So the whole eVTOL kind of paradigm that's emerged, they are viable technically. It's difficult with the regulatory environment and developing and the investment. But one of the things that I do know about from the skydiving case study is it's the cost of the batteries and the life cycle of the batteries. So how many cycles can you get from a battery, and what does that battery cost? Because the batteries are very expensive at the moment. If they were able to do, say, that mission that I talked about, 12,000 feet, even for a small aircraft like the Cessna 182, and you could get 2,000 cycles out of it, and it didn't cost much more than 20 or 30,000 pounds for the battery, then it starts to look okay. But if it's 1,000 cycles, it's not really okay. If it's 5,000, it's brilliant, because again, it depends a bit on the energy cost that you're putting in the electricity, and at the moment that's a fairly low factor. So they would be commercially viable right now if we had them. And then it just depends on how you scale it up into different missions and roles. And there's a real cutoff. So the next question there, if I go to that, which is related, about the relatively low energy density of existing battery technologies. So future commercial aircraft powered by hydrogen and ammonia fuel cells will well, yes, that's all we can look at the moment for large, heavy, longer range stuff. And they are both quite good prospects. There's a lot of issues with hydrogen in the supply chain, and some in terms of the distribution and the storage and everything. But and I can't really comment on the AerAeS class using this approach. But what I would say, before Jeff sort of might be able to answer that, is that the technology that comes to the DC link forward, so the inverter and the motor and the whole of the other system, whatever DC you put onto that, it's ready for. So if you had a fuel cell or another electrical generation technology, it's ready for that. Maybe not for the air-racing, but the technology that you've developed for the propulsion system is future ready for those other alternative energy storage devices. And Jeff, any ideas about how that could integrate maybe in racing?
Sorry, which part of that? That was
hydrogen
a
or
answer.
ammonia
I'm not
fuel
sure
cells.
which. Sorry?
Hydrogen or ammonia fuel cells as an E-RACE class.
Yeah, every so often I think about that and I brainstorm it with our team and we kind of put some notes down on paper and then we set it aside. Only because, we can only focus on one thing at a time. As it is, we're looking at the open class, performance class, building our own aircraft, and the eVTOL class. So we don't want to get too spread too thinly. I think it's a very interesting and fascinating idea. And ultimately, what RAeS's mission is, above all, is to do something relevant to the aerospace industry and meaningful for the aerospace industry and sustainability. So as long as hydrogen, fuel cells, and any other technology is important to the aerospace industry, we are here to provide a platform for them to test it. So the short answer, yes, but it'll be a couple iterations down the road.
Good. Thank you very much. There has been one other question. So the question is, Formula One cars fail mid-race. Has this happened to the AerAeS? I guess, do you have crashes and incidents then?
Yeah,
exciting.
No, we should talk about that. Safety, I should mention, is always at the highest priority of everything we do, not only in the engineering, but of course in the running of the race. So that's always front and center and paramount at all times. And yes, indeed, of course, there can be emergency situations during a race. Quite likely, as we anticipate, much less so in the electric than in the combustion, due to the reliability of these motors. But of course, there could be a battery fire, et cetera. And we're looking at containment systems for those. But even on the conventional side, we do have engine failures and other types of emergencies. And frankly, what happens is we for that reason, we race at airports. That's strictly where we race, is at airports. And we're racing a very confined area. The circuit's very small. It's a 5 kilometer distance, total distance, so about 1.5 kilometers, 2 kilometers end to end. So it's all right there. You can see the whole race, which is exciting, but it also makes it compact, and it's right next to the runway. So what happens is, if an aircraft experiences overheating or anything that they're not happy with, immediately they pull up and inside the circuit, inside the oval, and then up as high as they can. They just convert, their speed to energy, or their energy to height, I should say. And then they'll have enough distance to be able to come back and glide to a landing. So it's fairly common, but it's also extremely, extremely routine, and they train it and practice it. They're quite conditioned, and it's a reaction that they do. So it's a lot safer than it looks or sounds when you imagine air racing.
And I think then the very last question is really good then. Okay, when's the first race?
Yeah, it's going to be in 2023. Admittedly, we had hoped to be able to race between now and 22 a year or two ago, and COVID did delay us. I hate accepting that, but I have to say that COVID did set us back due to supply chains and some other things. It was what it was. But we're now set on a course to race in 2023. But we are going to have, as we mentioned, some test flights and individual aircraft taking to the skies throughout this coming year, and even this year potentially. And we're going to be doing training events, qualifying events, and lots of other activities. So we're not going to be without air racing of some kind this year. And of course, we do the RAeS 1. That's continuing. But RAC 2023.
Great. Thank you very much. Well, thank you, Richard and Jeff. It was really interesting. And I said it right at the beginning, I didn't know anything about it. So I've certainly learned a lot more about the topic itself. And I hope that all of the delegates who've been listening to have enjoyed your talk. Thank you very much, the two of you.
Thank you. Thanks to everyone.
Thank you. It's a pleasure to be here, and thanks for getting us on.
Yeah, and get in touch, everyone. Reach out to us.
Thank you very much. Thank you. And with that, then we'll close this seminar. Thank you very much, everyone. I have also put in the chat a link for a CPD certificate for those who might want a certificate. You can download it. You have to add your own name and date of the event. Thank you very much. Thank you.
Cheers.
With that, I think we can say goodbye. Yes, goodbye. Thank you, Richard. Thank you, Jeff.
Okay, take care. Bye.
Bye-bye. Bye-bye.
See you.
Bye-bye, Richard.